Welcome back, everyone. In this lecture, we're going to discuss edge detection. We're going to specifically talk about the Canny edge detector, which is one of the most popular edge detection algorithms. It was developed in 1986 by John Canny, and it's actually a multi-stage algorithm. So I'm going to quickly show you the actual steps that happen internally with the Canny edge detection, but when we actually implement it, we won't really see that much of it. It's just going to be a simple one-line call of OpenCV. So don't worry too much if you kind of don't understand all these steps, since it's pretty high level just seeing it in text instead of reading the full paper. But if you're really interested in the multi-stage facet of the Canny edge detector, then check out the resource link for the Wikipedia article, which actually explains all these steps, and then also the paper itself. Okay, so I'm just going to briefly just show you and explain the steps that are taken. The first step in Canny edge detection is to apply a Gaussian filter to smooth out the image in order to remove noise. Keep in mind, as we mentioned in the blurring and smoothing lecture, when you're applying edge detection on an image that has a lot of going on in it, maybe has lots of background noise or just a lot of background features and a lot of foreground features, you may end up detecting way too many edges. So most likely you're going to have to apply your own smoothing and own blurring technique first before the one that's built into the Canny edge detection. But just want to mention that. So after you apply the Gaussian filter to smooth out the image, what happens is you find the intensity gradients of the image. Then the next step in the Canny edge detection process is the algorithm will apply non-maximum suppression to get rid of spurious response to edge detection. Then it's going to apply double threshold to determine potential edges. And then it's going to track edge by hysteresis, which is just going to finalize the detection of edges by suppressing all the other edges that are weak and not connected to strong edges. So essentially, it's kind of a filtration process of getting rid of the weaker edges and only finding the really strong ones. Now, keep in mind, as I mentioned, for high resolution images where you only want general edges, it's usually a good idea to apply your own custom blur before applying the Canny algorithm. And we're actually going to show that right now when we jump to the Jupyter Notebook. Keep in mind, the Canny algorithm also requires a user to decide on low and high threshold values. In our notebook, we're going to provide an equation for picking a good starting point for threshold values, but often depending on the image, you're probably going to need to manually adjust that low and high threshold just to see what looks good and what edges make sense to you. So it is a bit of a manual process at first in deciding the low and high threshold values, but hopefully the equation we provide gives you a good starting point. Okay, let's begin exploring all of this in JupyterLab. Okay, so here I am in my Jupyter Notebook, and I went ahead and ran the several imports that we usually do. And then what I'm going to do is I'm going to read in the image. And in this case, the image I'm going to read in is imread, and we're going to work with that puppy dog face, which is sammyface.jpg. And let's go ahead and show that image. In this case, I'm not worrying about performing color correction on this image because I'm only performing edge detection. I don't really care if the blue and red channels happen to be switched. Let's first show you how you can run the Canny edge detector, and then we'll talk about different ways to try to get better results. If you want to just straight up run the Canny edge detector, just say cv2.canny, and then you provide the image you want to run it on, and there's two main parameters. There's threshold 1, and then there's threshold 2. We're going to start off by just setting these both as the middle value of what a pixel can be. So a pixel can be between 0 and 225. So we'll set them both to be the medium value, and we'll see how that works. So if we just show these edges, we can already see right off the bat, it tends to actually get the edge and general outline of the dog. So I can see Sammy's ear here, a little bit of its mouth, but it's also picking up a lot of edges that are probably just noise. So there's two different approaches we can take to this, and we're probably going to have to use a combination of both. One is actually blurring the image to get rid of certain details and just get general edge detection. And the other one is playing around with the threshold values. And you can go ahead and just play around with threshold values right now if you wanted to. So we can make the min and max just 0 and 255 and see how that performs. And you'll probably notice that it also doesn't perform super great, but it tends to actually pick up some stronger edges. So there's a little bit slight differences between these thresholds versus these ones in the middle. But let's go ahead and show you a formula that may help you out for choosing a threshold. In particular, after you've blurred the image, this formula tends to work quite well. So the first thing we're going to do is calculate the median pixel value. So I'm going to say that the median value of my pixel is NP median, and then I'm going to pass in the image, and it looks like my median value is 64. So it's actually not a super bright image, or at least it doesn't have very strong values in any particular color. Then we're going to set a lower bound threshold and the upper bound threshold, essentially threshold 1 and threshold 2. And a really common formula for detecting these thresholds is to actually just do a comparison between the lowest possible versus some sort of percentage of the median value. So you'll often see a formula like this: integer of the max value between 0 and 70% of the median value. So what this is doing is it's saying set the lower threshold to either 0 or 70% of the median value, essentially 30% below the median, whichever is greater. So 0 right now, that's our floor. If this value, 70% times the median value, happens to be a little higher, then we'll go ahead and choose that one, and that sets our lower threshold. And we're going to do something really similar for the upper threshold, except we're going to go in the opposite direction. We're going to set this to be the smaller between the absolute limit of 255 and then 1.3 or 30% above the median value. So the way to read this one is the upper threshold. Set that to either 130% of the median, so 30% above the median, or the max value of 255, whichever is smaller. Because if we go above 255, we no longer want to choose 1.3 times the median value. Something to note here, again, 64, that's a pretty low median value. So we may probably have to even adjust the upper limit a little higher. Okay, so we'll go ahead and run those thresholds and see if that improved anything. In this case, I don't believe it actually does. So I'm going to copy and paste this canny edges command, paste it in here, and then we have threshold, and we're going to set that to lower and upper respectively. You can go ahead and run that. And it actually didn't look like it improved anything. In fact, it's almost performing worse. We can see here that's detecting way too many edges. And something you may want to do then is if you actually take a look at the upper limit, that's going to be 83, which is quite low. So you may want to begin starting adjusting things like expanding the upper threshold limit to go higher and higher. So maybe as you go plus 100, it begins to generalize a little bit more. But really, the thing that's actually going to help you here is blurring the image first. So let's go ahead and blur that image. And you can use any of the blurring techniques that we've learned about already. But I'm just going to use CV2 blur and apply just a kernel to it. So we'll say image, and then the kernel size for the blurring kernel, I will say that's a 5 by 5. And now I'm going to, again, copy and pasting that edges, but instead of doing it on my image, I'm going to do it on my blurred image. And I will use the upper and lower ones that I calculated earlier. So we'll say lower and then upper. So now when I run this and I see the edges, now I'm definitely seeing the stronger edges of the dog's face. And in fact, this is probably the best one we've seen so far. If I compare it to the other ones, they're still picking up a lot of noise. So compared to the original image, the one that's really showing the strong edges of the dog's face is this last one after we've been able to blur the image a little further. And if you want, you can then experiment also with the kernel size here, maybe expand it, see if that continues to blur the image until you only see what you're looking for. And what you can also do is then expand maybe the upper limit here to like 50, and let's reduce this kernel size. That's probably a little too blurred. Do a 5 by 5 there. Run this, and you can begin to have some sort of happy medium where you're detecting the edges you want to detect without detecting too much noise around it. So again, we can clearly see here the dog's face. Okay, main things to know here is just call cv2.canny, pass in your image, and then using these formulas, you can play around as good starting points of your lower and upper threshold, but more likely than not, you should blur the image and then also play around with the threshold amount until you see something satisfactory. Thanks, and we'll see you in the next lecture. Welcome back, everyone. In this lecture, we're going to briefly talk about grid detection, specifically the two built-in functions that are in OpenCV that can help you find grids if the need arises. often cameras can create a distortion in an image, such as radial distortion or tangential distortion. And a good way to account for these sort of distortions when performing operations like object tracking is to have a recognizable pattern attached to the object being tracked. So often what you'll see happen is if you're trying to track maybe a car using some sort of CV application and you're just training the actual application to work, then you'll put a grid-like pattern on the car so you can keep track of the angle of the car as you go along. So here we can see an example of grid tracking where there's a cube mounted virtually onto this grid that is in real life. As the grid moves, that cube will then be tracked. So grid patterns, they're often used to calibrate cameras and track motion. OpenCV has built-in methods for tracking grids and chessboard-like patterns. Let's go ahead and just quickly explore them with the chessboard images that we've already seen. Okay, here I am in the Jupyter Notebook. I went ahead and just did the normal imports, although we won't be using them all. We will be using CV2 and Matplotlib. The image we're going to be working with is that flat chessboard image. Let me go ahead and load it again. We'll say CV2 image read, and then data, and the one we're going to read is called flat chessboard. And let's go ahead and just display that image so we can see what it looks like. We'll say flat chess, and then just run that, and there we have the image itself. Something to keep in mind here is for this sort of grid detection, this particular grid detection methods we're showing here, the grid has to essentially look like a chessboard or be a formalized grid. This is not looking for something that kind of looks like a chessboard or kind of looks like a grid. The grid should be specifically made to look like some sort of checkerboard or chessboard type image and then placed on whatever you're trying to calibrate your camera with or whatever you're trying to analyze. So keep that in mind. It's really only specifically looking for this sort of pattern. Okay, so how do we actually find the chessboard corners? Well, we just call CV2 and then say find chess. And if you hit tab here, it's going to autocomplete to find chessboard corners. Again, this is just specifically looking for things that look like a chessboard grid. You pass in the image. So we pass in that image variable, and then you pass in the grid size. In our case, the entire image is 8 by 8, but it's not going to be able to detect the outer chess squares because they're missing an edge since they're all the way to the end of the image. So instead what we're going to do is for the second parameter, which is the size of the grid, we will say 7 by 7 because since this is 8 by 8, it's not going to be able to detect that very last one. So let's say it's 7 by 7, and it returns back two variables which we can unpack, found and corners. Found is just a really useful Boolean indicating whether or not it was able to find the chessboard type corners. So often if you're kind of dealing with something that looks a little sloppy or a little blurry, it will say found is false and then it won't return anything in corners. So it's nice to be able to use found as an if statement. So if found, print we found corners, else print we did not find corners. If you take a look at the actual corners object, it's essentially a list of coordinates that show you where it actually found the corners of the chessboard. And we're going to be able to use that in conjunction with another function called draw chessboard corners. Let's go ahead and do that. I'm going to say CV2 and then type out draw chessboard corners. Go ahead and tab autocomplete that. We're just going to pass in our image. So we're going to say flat chess, or you can also make a copy of this. And then we'll say the following. We'll say that it was 7 by 7, pass in the corners, and then you also pass in found. So basically, this algorithm, or the find chessboard corners function, feeds directly into the draw chessboard corners. And we can go ahead and do that. And that will draw on place on this image. So sometimes you may want to make a copy if necessary, but let's see the results. I'm going to say plt imshow. And when we run that, we get to see the flat chessboard image. And now we see the OpenCV draw chessboard corners. And what it does is it just marks the corners, and then it marks the rows in different colors. So you kind of get this rainbow-like row, and it ends up connecting them all with a zigzag line that looks like this. So it follows along, and then it connects to the next one, and it looks something like that. Okay, so two really simple and easy to use functions. The main thing you have to be worried about is if your image is actually clean enough as a chessboard to read. This one's really easy because it's literally just a kind of two-dimensional cartoon chessboard, but often in real life it's a lot trickier, which is why this found variable will be useful to use as an if statement of whether or not you can actually perform the draw chessboard corners. Now, we can actually look for other grid-like patterns. Another common grid-like pattern are circle-based grids. So I'm going to load up another image called dots and say CV2 image read data, and this one is called .grid.png. Let me just show you what it looks like first. We can see here we have a grid of dots. This is another really common pattern, just a grid of circles or a grid of dots. We can see here that even these aren't like perfectly clean circles, and we're going to have another function that can find these as well. This one is called CV2 find circles grid. And then we're going to pass in dots, and then you're going to pass in the dots you're actually looking for. So in this case, if you count them up, we're looking for a 10 by 10 grid. And the final parameter here is the way it actually searches for it. We're going to use the default value, which is the way it calibrates to find it. It's calib underscore CB underscore, you can kind of tab autocomplete this if you want, CB underscore symmetric grid. So just looking for circle grid, this is the actual method it's going to be using. Go ahead and run that. Check that it actually found them. And found is true. So it found the actual grid, which means we can then actually draw on this as well. And these corners are actually in the same format as the corners from find the chessboard image. So then we can actually use the draw chessboard corners function, even if we were looking for a circles grid. So I'm going to copy this. And then let me come back up here. I'm going to comment that out. I'm going to copy draw chessboard corners. And in this case, we're going to draw on the original dots image. It was a 10 by 10 grid of dots. And then we just pass in corners and found. We'll go ahead and run that. And then after you see this array, what's going to happen is I can actually show the resulting image since it was drawn on. And let's go ahead and check it out. It should be dots. And then we can see all the dots. So it ends up plotting it each with a particular color, and then each new row gets a new color of the rainbow, and so on. And that's how the draw chessboard corners works. Okay, so this is often used for camera calibration. We've really only scratched the surface here. The main reason we want to show this lecture is because it's a direct extension of finding corners and finding edges. It's just two functions that are conveniently built into OpenCV. Again, CV2 find circles grid, and then CV2 find chessboard corners. And then if you ever want to draw on the original image, you can say CV2 draw chessboard corners. It returns this array, but also will affect and draw on the image you pass in. Thanks, and we'll see you at the next lecture where we begin to talk about contour detection. Welcome back. In this lecture, we're going to discuss contour detection. Contours are defined as simply a curve joining all the continuous points along the boundary having the same color or same intensity. Contours are a very useful tool for shape analysis and object detection and recognition. OpenCV has a built-in contour finder function that can also help us differentiate between internal and external contours. It has a lot of functionality packed into just a simple function call. Let's go ahead and take a look. All right, here we are at the Jupyter Notebook. I'm going to read in from my data folder an image called internal underscore external. So if you start typing in, you should see internal underscore external.png. And as a second argument, I'm going to pass in a 0 to read it in as a grayscale. And if we check the shape of the image, notice it's just X and Y. There is no color channels. So let's see what this image actually looks like. And I'm going to map this in grayscale. And it's a pretty simple image. The main things to notice here is that we have a triangle, and the foreground space is white and the background is black. Then what's interesting is we have a smiley face with 2 black circles for eyes and a black circle here for the mouth. And then we have kind of like a pizza pie shape here with a bunch of pepperonis on it. And what we're going to do is we're going to be able to find and extract contours. What's really cool and interesting about the find contours function of OpenCV is that it can actually detect internal contours, such as these pepperoni slices or the eyes or the smiley face, versus external contours, such as the circle, the triangle, or this circle with a wedge cut out of it. And what we're going to do is we're going to use the find contours function. And the way we do this is we simply say CV2 dot find contours, and you can tab autocomplete that. You pass in the image that you want to analyze. And there's a couple different metrics or ways to actually find contours. So there's built-in functions, and if you say cv2.retr underscore and then hit tab, there'll be some different ways here to actually find the contours. The one we're going to be using is CCOMP, so complete. And what this does is it's going to extract both internal and external contours organized in a two-level hierarchy that you can then index and call off of. If you're only interested in internal contours or external contours, there's other methods here. For example, you can use external to only grab external contours. Right now, we're just going to use this complete one that grabs all the contours for us. And the third parameter here, if you do Shift Tab, that's going to be the actual method. We're just going to be using chain underscore approx underscore simple as our method. Okay, and this is actually going to return back a few objects. It returns back an image, the contours themselves, and then the hierarchy that organizes them. The hierarchy depends on actually what type you call, but in this case, since we're calling for both internal and external contours, we're also going to return a hierarchy here. So let's run that. Let's check out what these actual objects are. If we check out the type of contours, it's a list, and then the length of contours is 22. And if you were to count out these actual contours, such as the number of pepperoni slices, the circles, the eyes, and the smiley face, you would get 22 contours. And if we check out the type of hierarchy, so let's check out that. Hierarchy is a NumPy array. And if we actually show you what it looks like, it's essentially a bunch of lines that define where the contours are, and then a parameter that actually defines whether they're internal or external. So let me show you how you can actually then use contours here and hierarchy here to show external contours versus internal contours. It's a bit strange because you kind of have to know the way it's organized. So we provided some code for you in the notebook. That way you can just have that skeleton code to reference. So I will set up an empty array, and I'm going to call this empty array just external contours. And this is going to be just zeros in the same shape as the image. And this can be image or IMG. It doesn't really matter. It's the same thing. So if I check out external contours, shape, there it is, 6521080. And if we check out the original shape, 6521080. Okay, so the image returned back, that's basically the same thing. In fact, we can actually show it. Image here, it's essentially the same thing. Okay, so now that we have this NP zeros, this is going to be external contours, just a pure black in the same shape as the original image. Now what I want to do is actually draw the contours on. And there's a draw contours function within OpenCV. The only thing is I have to know how to actually read and understand this list of contours using the hierarchy. So what we're going to do, and typically you don't really memorize this, you just reference it from either the documentation or notes like the ones we provide for you. We're going to say for I in range of length of contours. So remember I in range of length of contours, if we actually check what this is by passing this in to a list, that's just a list of numbers. So for 0, 1, 2, 3, 4, 5, all the way to 21, the length of contours, because since we have 22, but we're also counting 0, that works out. So we have for I in range of length of contours, if hierarchy, and then we're going to do a little bit of indexing here. We're going to say 0, I, 3, and then equals equals -1. Essentially what that is doing is it's indexing for each of these rows this last column right here, this -1 or 0. So, or it can also be 4, depending on what type of contour it is. Again, we're just checking out the last column here. That's what this indexing is doing, and with the I, it's doing it for every single row. So we're checking if the hierarchy value at that particular column is equal to -1, then that means it's an external contour. So it's external. If it's not equal to -1, then it's internal. So we have -1 there. It's an external contour. And then what we're going to do is say CV2, draw contours, and we're going to draw external contours, and then I, 255 for white, and then -1 so it's actually filled in. So let's run that. So what this did is it went through that contours list, and then it checked, hey, if the hierarchy for that corresponding contour, and if we actually check out the list of contours, we can show you. These are essentially just arrays that define how to actually draw the contours. So it's saying, okay, for that contours, check if the hierarchy is good. If it is, then onto this black external contours, remember that's the zeros here, go ahead and draw that specific contour, and then we'll be able to view it. So let's actually view the external contours. We'll say PLT imshow, external contours, and let's make the CMap gray. And here, with defined contours and the hierarchy, where it's equal to -1, it actually detected the external contours. So these are things that are actually directly touching what it believes to be the background. So this triangle, the circle, and the circle with the slice taken out of it, those are all external contours because their boundary is touching the actual background. Now, the internal contours were things like, if we come back to the original image, these guys right here, the pepperoni slices and the eyes and the smiley face, the edges of those contours, they're actually not touching the background, they're touching a foreground object. So those are known as internal contours. And what we can do is essentially run this exact code, but then instead of where it's equal to -1, we're saying not equal to -1. So I'm also going to redefine this external contours, but we're going to make it internal. So let's grab that, paste it right here, and we will say internal contours. So basically following the same process, I'm creating a default black object that I can draw on, just an array. And then for all the contours, what I'm doing is for internal, what I will say is if that third column is not equal to -1, then it's an internal contour. And I'm going to draw it onto my internal contour. And let me make sure I have that right. Yep, internal contours, contours I25. So let's go ahead and run that. And then let's show the internal contours. Internal contours, CMap is equal to gray. Run that, and then it went ahead and displayed the internal contours. And there you have it. So that's how you can actually then use find contours and draw contours to display contours. The last thing I want to actually note here is the way that works with the hierarchy. It can actually then define this set of contours as different than the smiley face. And if we come back up here, you'll notice that in this last third column, we have -1s. Those are the external contours. We have these 3 zeros. Those are the eyes and smiley face of the eyes and smiley face of the actual smile. And then we have 4s. Those are all the pepperoni slices. So you'll notice that it actually numbers them differently depending on a grouping of internal contours. So if they're within different external contours, it will group them differently. So what I would encourage you to do is we can then test on this by saying, only give me where it equals 4. And let's rerun this again. So we're going to say now, let's redefine, I'm going to rerun this cell, external contours. Check the shape again, that's looking good. And now I'm only going to do it where it equals 4. And then let's see how that works. So those are all the pepperoni slices. Now let's try it again, but this time I'm going to choose just where it equals 0. So we will say 0 there. Let's rerun this so we get the fresh background. Run these again. And now I only get the smiley faces. So what's really cool is not only does it give you organization between internal and external contours, it also gives you organization within the internal contours themselves, depending on what external contour they were found inside. So that way, maybe if you, for some reason, only wanted to display the internal contours of a particular object, such as a smiley face, you can go ahead and do that. Okay, so that's it for this lecture, and we'll see you at the next one.